Hi everybody, my name is Aphrodite and today I'm going to be talking about recent neutrino cross-section results using data from the MicroBooNE detector. But before we dive into the details of our latest results, I would like to quickly remind everybody of the fact that neutrino physics is about to enter a new era of high-precision measurements with forthcoming experiments like DUNE that will try to extract the oscillation parameters and to determine the mass hierarchy. For these high-precision measurements to take place, we will be using state-of-the-art detectors such as liquid argon time projection chambers, but at the same time, we must be able to provide precise neutrino cross-section measurements on complex nuclei such as on argon. And the reason why our cross-section measurements are extremely important is because of the way that a neutrino oscillation experiment works. What happens in this case is that we get started with neutrinos at the source, some of those neutrinos interact in our near detector, and the remaining ones cover some distant cell until they reach our far detector, at which point some of them have oscillated into a different flavor. In both cases, what we measure is the number of interactions, and this event rate depends on a fairly complicated expression which includes the fluxes, the cross-sections, the selection efficiencies, and the oscillation probabilities that we want to measure with high precision. But at this point, it becomes pretty clear that if we want to make a high precision oscillation probability measurement, we first have to have a really good handle over every other quantity included in this expression, and that means that making high precision cross-section measurements is a prerequisite. The great news in this case is that we don't have to wait for experiments like DUNE to start taking data before we are able to make those high precision cross-section measurements. The reason for that being that we can already get started with experiments of the short baseline neutrino program. The reason for that being that all those experiments will be using the same detector technology, namely liquid argon TPCs, which are ideal for making detailed measurements of complex topologies. Out of the experiments of the short baseline program, MicroBooNE is the one that has already recorded a wealth of neutrino scattering events over the course of the past 5 years, which means that we have available in our hands the largest neutrino argon scattering dataset. A few more details when it comes to our experiment. MicroBooNE is located at Fermilab, roughly 500 meters away from the source and between the SPND near detector and the Icarus far detector. Because of the location of our detector, we are getting neutrinos from two beam lines, namely the booster neutrino beam, which is on axis and is dominated by muon neutrinos with an average energy of about 1 GeV, and at the same time from the NUMI neutrino beam, which is off axis, and we have a much richer contribution from electron neutrinos, also with an energy of about 1 GeV. Neutrinos from those two beam lines enter our detector, and some of them interact with the argon nuclei. Out of this interaction, we have the production of charged particles that further ionize the material, and that results in the production of ionization electrons, which in the presence of a strong electric field, drift towards the anode, where we have three wire planes and more than 8,000 gold-coated wires with a wire spacing of 3 millimeters. Apart from the ionization electrons, we also have the production of scintillation light, which is collected by 32 PMTs, which are located behind the anode. With this information in our hands, we can reconstruct pictures like the one that you can see on this slide, which is what we would call a MicroBooNE event display. What happens in this case is that we have an invisible neutrino entering our detector from the left, interacting with an argon nucleus, and out of this interaction, we have the production of a long, minimally ionizing muon track and multiple highly ionizing proton tracks. These event displays are expressed in coordinates of time versus wire, with the time component being indicative of the position in the direction perpendicular to the beam line and the wire component being associated with the position along the beam direction. And another thing that I wanted to highlight in this case is that the color scale on our event displays is associated with the charge deposition in our detector. So with this detector technology in our hands, we can push the particle detection thresholds to even lower limits. We have precise calorimetric information because of the charge deposition in our detector, and 4 pi coverage, which means that we have high statistics. So with these datasets available in our hands, we have already produced a wealth of neutrino argon scattering results that include charge current inclusive cross-sections using both electron and muon neutrinos, and for that we reported flux averaged, single differential, and double differential cross-sections to more exclusive channels using muon neutrinos, with topologies in the final state that include neutral pions, topologies with multiple protons and no pions, a quasi-elastic-like measurement, and even neutral current interactions with a single proton in the final state. So let's take a closer look at our measurements. And in order to visit the first of our measurements, I would like to quickly remind everybody of one of the greatest advantages that we have in the context of a liquid argon TPC detector, which is the discrimination power between electrons and photons. The reason why this is extremely important is because both particle species create showers in our detector, but it is very important to isolate them. The reason for that being that such showers are going to be used for electron neutrino appearance searches in the context of the SBN program and eventually for DUNE. And at the same time, photons from decays of neutral pions are going to constitute the dominant background for those appearance searches. But the good news in this case is that with our liquid argon TPC technology, we can discriminate between the two particle species using two key elements, namely the deposited energy and the distance between the interaction vertex and the start point of the relevant shower. And when it comes to the photons in our detector, they deposit an energy of about 4 MeV per centimeter, and there is a clear separation between the interaction vertex and the shower start point, and this is exactly what you can see in the event display included here on the left. This ability to identify photons in our detector is the one that led us to the first measurement of flux-aberrant cross-sections on argon with topologies that include neutral pions in the final state. On the other hand, we have the electron showers in our detector, and electrons deposit half the energy compared to photons, which is exactly what you can see in the figure included here on the left, showing the energy deposition per unit length for the leading shower with a green histogram showing the electron contribution with a clear peak at around 2 MeV per centimeter, unlike the photon contribution corresponding to the red histogram and a peak deposition at about 4 MeV per centimeter. And another thing that we can take advantage of is the fact that the electron shower start point is attached to the interaction vertex, which is exactly what you can see in the event display included here on the right. So with this discrimination power available in our hands, we performed our first inclusive measurement using electron neutrinos and antineutrinos using the NUMI beam line. The reason for that being that the beam line is much richer in electron neutrinos to boost our statistics. The selection resulted in the largest ever sample of electron neutrinos on argon with more than 200 events, a purity of about 40%, and an efficiency of about 10%. The flux integrated cross-section that we reported for this analysis is shown here on the left and illustrates a good agreement between our data and multiple theory predictions that include two versions of the Gini neutrino event generator and a comparison to an alternative event generator, namely Neuro. We played exactly the same inclusive game, but in this case using new neutrinos and the BNB beam line, but in this case we took the discussion one step further and we performed the first double differential measurement on argon. The results that have been included at the bottom of this slide show the double differential cross-sections for mu kinematics as a function of the mu momentum, for backward scattering angles on the left, and for forward scattering on the right. What we learned out of this comparison is an overall good data Monte Carlo agreement with the more recent models, in this case corresponding to the blue line and one of the latest versions of the Gini neutrino event generator, being the ones that are doing the best job, especially as we move at forward scattering angles. However, if you take a look at the reported chi-square per degree of freedom, you can see that even more recent models actually result in ratios that are significantly greater than 1, which means that we need to take a look at more detailed topologies in order to investigate the source of the differences that we see in our inclusive measurements. The great news in this case is that this is entirely possible in the context of a liquid argon TPC detector, where we can detect protons in the final state, and on top of that, we can push the proton detection thresholds to even lower limits. And if we actually do that, we can probe more detailed interaction channels and nuclear effects, and for comparison, the exclusive results in MicroBooNE that I'm going to be talking about in a moment use a proton detection threshold at 300 MeV per se, comparable to the one used by Argonaut and lower than the proton threshold used by T2K and Minerva. And the way that we identify the protons in our detector is by using the energy deposition per unit length as a function of the residual range, and specifically by using the Bragg peak in the last 30 centimeters of the track. So that brings us to our first, more exclusive measurement on MicroBooNE, which includes an event selection with a muon above 100 MeV per se, at least one proton in the final state above the detection threshold of 300 MeV per se, and no pions in the final state. This event selection results in a purity of about 70% and an efficiency of about 30%. And in the results that have been included at the bottom of this slide, as a function of the proton kinematics, for the momentum on the left and for the angular distribution on the right, you can see that we have an overall good data Monte Carlo agreement. However, at this point, I would like to highlight once again that with our liquid argon TPC technology, we can push the proton detection thresholds to even lower limits, and on top of that, the bin which is closer to this detection threshold is actually the one which is most sensitive to the model differences. We can play exactly the same game as a function of the muon kinematics, once again for the momentum of the muon on the left and for the angular distribution on the right. And what we observe in this case is an overall good data Monte Carlo agreement, but the thing that I would like to draw your attention to in this case is the turnover that we observe in our data in the very forward scattering angle, as opposed to the rising trend that we observe by all of our event generators. But at this point, we have established that on MicroBooNE, we can detect multiple protons in the final state. So it makes a lot of sense to focus on a very specific interaction channel in this case. And in this case, we are going to be focusing on quasi-elastic interactions. The reason for that being that we are talking about a very simple topology, which is dominant at energies that are relevant for the SPN program. Once again, our event selection includes muons above 100 MeV per se, but in this case, we have the requirement for exactly one proton above 300 MeV per se. In this analysis, we have eliminated the cosmic contamination by requiring that the opening angle theta between the muon and the proton is roughly 90 degrees, and we have enhanced the quasi-elastic contribution by requiring that the opening angle phi between the muon and the proton is roughly 180 degrees, and that the transverse missing momentum, defined as the vector sum of the transverse components of the muon and the proton in the final state, is relatively small. The reason for that being that if this quantity is large, then most likely the candidate interaction originated from a more complicated topology instead of a quasi-elastic one. And with this event selection, we achieve a quasi-elastic purity of about 80%. So now we are ready to take a look at the single differential results for this analysis, and specifically as a function of the angular distribution for the muon. What we observe in this case is that we have an overall good agreement between our data and multiple predictions from event generators available in the neutrino community, with the exception of very forward muon scattering angles. But given that we have an overall good data Monte Carlo agreement across this distribution, the deficit that we observe in the very forward direction definitely affects the data Monte Carlo agreement as a function of other kinematic variables of interest, namely the momentum of the muon on the left, the angular distribution for the proton in the middle, and the momentum of the proton on the right. This is exactly the reason why this analysis was repeated twice, with the top panel corresponding to the results that we obtained for events using all the events that satisfy our selection criteria, and with the bottom panel corresponding to the case where we repeated the analysis after we excluded those events that fall into the very forward angular region. And if you make a comparison between the top and the bottom panels, you can immediately see that we get an improved agreement if the forward muon angles are excluded. So this gives us a very consistent picture which starts with a single differential measurement for our inclusive measurement as a function of the angular distribution of the muon, where what we observe on the left is an excess of our Monte Carlo in the very forward region as opposed to what we see in our data. This Monte Carlo excess becomes a data turnover the moment that we move to a more exclusive measurement on MicroBooNE in the exact same forward direction, and this deficit becomes maximum if we choose to focus on a very specific interaction channel, namely the quasi-elastic one. So this consistent picture concludes the discussion in terms of the already available results that have been released by our collaboration. But this is far from the end of our cross-section story. The reason for that being that over the course of the past 2 years, we have made a huge improvement in terms of the understanding of our detector, where we use signal from all planes, we have improved our calorimetry, and we have a much better reconstruction efficiency. We have also reduced our systematic uncertainties by using a data-driven method for vastly improved detector uncertainties, and we have suppressed the cosmic contamination in our samples by installing a cosmic ray tagger as of 2018 and by using the cosmic data as background to our simulation. And in order to illustrate the effect of the improvements that I just talked about, I would like us to revisit our inclusive measurement. So the picture that you can see here on the left shows the selected events as a function of the angular distribution for the MUN for our previously published measurement, and the picture on the right shows our current measurement after the improvements that I talked about have been included in our workflow. With these improvements that we talked about, we can boost the purity of our measurement from 50 to more than 70%. We reduce the cosmic contamination by almost a factor of 3, and we have suppressed our detector uncertainties from roughly 15% to about 3%. But apart from the fact that with these improvements we can make more accurate measurements, those improvements also allow us to take a look at more rare final states. And the typical example of that would be the topology that is featured on this slide, which would correspond to a neutral current interaction with a single proton produced in the final state, with a proton track with length between 1 centimeter and 2 meters, and this measurement constitutes the lowest Q-squared neutral current analysis to date. This event selection corresponds to a purity of 40% and an efficiency of about 30%, and can be used to measure the strange component of the neutral current axial form factor. So at this point, I would like to quickly summarize all the things that we had the chance to talk about today. And in today's presentation, I was given the chance to illustrate that cross-section measurements on argon are vital for the success of the SBN program and eventually for the success of WIN. On MicroBooNE, we have made huge progress in this direction over the course of the past 2 years by making measurements with low energy protons, neutral pions, electron neutrinos, and way more. We have also demonstrated that our liquid argon TPC technology has 4-pi acceptance, which allows us to make accurate measurements with exclusive final states. But this is far from the end of the story, because more and more precise measurements are expected to follow in the near future, which will allow us to further benchmark the performance of our models. And just to illustrate what I'm talking about, this is the wealth of MicroBooNE results that are going to follow in the near future, covering a really wide range of inclusive measurements, more exclusive measurements with no pions in the final state, exclusive measurements that result in the production of pions, and even more rare channels. And that brings me closer to the end of this presentation, where on behalf of the MicroBooNE collaboration, I would like to thank you for your attention.